Today we're going to look at the derivatives of polynomials, and we're going to look for a shortcut to differentiating things like x to a power, where we don't have to use the limit definition every time. So what we're going to do is we're going to start with a couple that we've already done, and see if we can figure out a formula for it. So if f of x equals c, if it's just a constant, 2, 7, negative 2/3, pi squared, something that doesn't have a variable, then we know that this is, if I graphed it, a horizontal line, right, y equals 2, and the derivative is the slope. The slope of a horizontal line is 0. So the derivative is 0. The next one we look at is f of x equals x. Again, this is a line, so the derivative is the slope, and we know the slope of a line in slope-intercept form, which this is, f of x equals 1 times x plus 0. The slope is the coefficient of x, which in this case is 1. So the derivative is just 1. The next one is f of x equals x squared. We've done this one a couple times, so it shouldn't come as a surprise that the derivative is 2x. The last one we're going to look at is f of x equals x cubed. So we can do this one out using the limit definition, and if we do, we get that f prime is 3x squared. So if we look at this pattern, pause it for a second and see if you can figure out what it is. Okay, so if I continue going down, I would have the derivative of x to the 4th is 4x cubed. The derivative of x to the 5th is 5x to the 4th. And in general, if f of x equals x to the n, then to find the derivative, we bring down the n as a coefficient, and then our exponent is our previous exponent minus 1. So if we notice, the exponents are always the coefficient. And then our new exponent is 1 less than the previous one. This is going to be true for any n, not just the positive integers that I've shown. So let's do a couple examples. We're going to look at f of x equals x to the 6th. So if I want to differentiate it, I take my exponent 6, bring that down as the new coefficient, and then the new exponent is 6 minus 1. So I get 6x to the 5th. As the next example, we have f of x equals x to the negative 3. So if I want to differentiate it, I bring down the negative 3 as my new coefficient, and I subtract 1 from my exponent. So I get negative 3 times x to the negative 4th. The next one is x to the 2/3. So again, I'm going to bring down the 2/3 as my new coefficient, and then my new exponent is 2/3 minus 1. So I get 2/3 x to the negative 1/3. f of x equals x to the negative 4/5. Again, the negative 4/5 will be my new coefficient, and my exponent will be negative 4/5 minus 1. So I get negative 4/5 x to the negative 9/5. Sometimes the function that we're given isn't in the form x to a power, and we need to do a little bit of algebra to rewrite it. So we need to remember that 1 over x to the n is x to the negative n, and the nth root of x is x to the 1 over n. So each of these two different equations involve a fraction, but what I tend to see is that people will put the fraction ones together, and they'll say 1 over x to the n is x to the 1 over n. So you remember there are two rules, one with fractions, one with radicals. Each of them involve a fraction, but neither of them involve both fractions. So 1 over x to the n is x to the negative n. The nth root of x is x to the 1 over n. So we're going to use this rule to differentiate the next two examples. Y equals 1 over x to the 5th. So this is a fraction. I want to bring up my x to the 5th, and I'm going to do that by making the exponent negative. So y is x to the negative 5th I haven't done any differentiation yet. It's still y. I haven't done y prime. A lot of people will just say that it's x to the negative fifth and then be done and call that the derivative. So all we've done is rewritten it. To differentiate it, I now take my exponent of negative 5, bring it down as the coefficient, and raise x to the negative 5 minus 1. So I get y prime is negative 5, x to the negative 6th. The next one is y equals the 7th root of x. So I'm going to rewrite it. The 7th root means something to the 1 over 7. So I have x to the 1 over 7. When I differentiate it, 1 over 7 will become my new coefficient, and the exponent is 1 over 7 minus 1. So I get 1/7 x to the negative 6/7. The next thing we're going to look at are derivatives of products of constants and functions, and also the sum or difference of functions. So if u is any differentiable function, c is a constant, so again 3, 2, negative 2/3, e to the 4th, something that doesn't involve the variable. Then if my function f of x is c times my original function u, then if I want to differentiate it, I just bring out the c, differentiate u, and then multiply back in the c. And then similarly, if I have the addition or subtraction of functions, if I want to differentiate it, I just differentiate term by term. So if I have the function x squared plus x cubed, I would differentiate x squared, I would differentiate x cubed, and then I would add them together. So we'll do a couple examples of these two new rules. So y equals 6x cubed. So I'm going to pull out the 6, differentiate x cubed, so I get 3x squared, and then I'm going to multiply back in the 6, and I'm going to get 18x squared. For the next one, I have f of x equals 2x to the 8th minus 3 times the square root of x. So again, the first thing I'm going to do is rewrite it so that I have x to a power instead of the radical sign. So I get 2x to the 8th minus 3 times x to the 1/2. So remember, the square root, there's no number written there, but it's an invisible 2, not a 1. So it's not x to the 1 over 1, that's just x to the 1, which is just x. This is the square root, square meaning 2. So it's x to the 1 over 2. So again, I'm going to pull out my coefficients and differentiate just the x to the power. So x to the 8th becomes 8x to the 7th, and the x to the 1/2 will become 1/2 x to the negative 1/2. Then I'm going to clean this up by doing out the actual multiplication. So I get f prime of x is 16x to the 7th minus 3/2 x to the negative 1/2. And we're going to do 4 more examples. So g of x is 14x cubed minus pi x squared plus 2x. So again, I'm going to have 14 times the derivative of x cubed, which is 3x squared, minus pi times the derivative of x squared, which is 2x, plus 2 times the derivative of x, which is 1. So I get just 2. Then I'm going to simplify it, and it's going to become 42x squared minus 2 pi x plus 2. For b, we have h of z equals 1 over 2x cubed plus e squared. So that should really be the same variable, either both z's or both x's. Okay, so just keep that in mind. So the first thing I'm going to do is rewrite my 1 over x cubed as x to the negative 3. Notice the 2 does not move. The 2 is not being raised to the 3. It is still 1 over 2. So I have a half x to the negative 3 plus e squared. When I differentiate it, I'm going to bring down the negative 3, so I'll have 1/2 times negative 3, so that's negative 3/2, and then x to the negative 4. E squared is a constant, right? E is 2.71, blah, 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 blah. It is a number, there's no variable there. So the derivative of a constant, remember, is 0. So it's not 2e, like I have a lot of people tell me. E is not a variable. It's just 0. So I just have that one term there. For C, we have L of x equals 2x squared minus 10x plus 1. And we want to find the derivative at x equals 2. So we haven't done one of those yet, but we've done them in the past. So the first thing I'm going to do is differentiate the function. So L prime of x would give us 4x minus 10. So again, 4x from 2 times 2x, and then minus 10. The derivative of 1, remember, is 0. So to find L prime of 2, everywhere I see an x, I'll plug in 2. So I have 4 times 2 minus 10, which gives us negative 2. And then our last example is S of t equals 1/3 t cubed minus 2.5 t squared. And again, we're going to differentiate it at t equals negative 1. So S prime of t, I'm going to bring down the 3. So 1/3 times 3 is 1. So I get 1t squared minus 2.5 times 2t, which is negative 5t. And I'm going to plug in negative 1. So negative 1 squared minus 5 times negative 1. And that's going to give me 6. Negative 1 squared is positive 1. And then when I subtract 5 times negative 1, it becomes plus 5. So 1 plus 5 is 6. So there you have it, a nice shortcut for differentiating polynomials. So if you have any questions, shoot me an email. Otherwise, try the homework. Let's see how it goes, and good luck.